start. So it's a pleasure to have today as a first speaker of the joint seminar with Princeton University, Alexis Vasseur from the University of Texas Austin, and he will talk about limit of Navier-Stokes to Euler for small BD solutions. Compressible, I guess.
Compressible.
Yeah.
Thank you, Camillo. Thank you for the introduction. Thank you for the invitation. It's a great pleasure to be here. And before I forget, so I should mention my collaborators, Bianchini from Kansas and Moonjin Kang from KAST in South Korea. Okay, so I'm talking about several things. Well, I'm talking about compressible fluid, Euler. So I mean, the focus will be on Euler. So it means with shocks, right? And well, when you have shocks, after shocks, well, a general idea to say, well, justify in some way the solution of PDEs with discontinuous solution is to say, oh, but they came from a physical model. When you add more physics, right? And a very natural way is say, well, let's take it as a limit of Navier-Stokes equation for a small viscosity. And surprisingly, well, it's not that simple. That's what I will try to convince you. And one of the reasons is actually because viscosity, which regularizing, is something which is bad for singularity. So there is a destabilizing effect. And I will talk about this limit, which was open for quite a long time, but only in the 1D case. So I will consider a very simple solution, very simple static problem, but open for quite a while. So my equation here, I will take really the simplest one. So you take a biotropic Euler equation. I guess I don't have much to say here, but the first equation, so the unknown is density, momentum. You take the continuity equation, and you have a pressure like rho gamma. That's it. And basically, I want to consider the viscous approximation of that, which is exactly the same system, but when you have the diffusion, and the diffusion here, well, for some technical reason, I want actually to have a diffusion which is a function of rho here, and I will talk a bit about that. So I put it right away here. But what is important is the viscosity coefficient mu, which is supposed to converge to 0, right? And we want to recover the solution of Euler when mu converge to 0. Everything is based on, I mean, a lot of things that we'll talk about is based on entropy. So I'll just rewrite the entropy here for the system, which is actually also an entropy for the Navier-Stokes. I call it an entropy, but it's actually the energy, right? And it's because we work with the biotropic. So it's the kinetic energy plus the internal energy. But I will use it as a mathematical entropy. That's why I call it entropy. Okay. And I go back to putting a bit in a general package. I mean, is just because it's easier to write, and then I will be able to talk a bit about what's done before. So I mean, this is typically a conservation laws here written in 1D. And now this means that, well, because when 1D is the time is R plus, the position is X, but I consider a solution of my U is vector, right? So that's the same, consider vector here. So it will be Rn, n is the number of equations that you consider. Here I will consider n equal 2. And then we consider only such system when you have an n-dot convex entropy. And so, well, the new question here. So just to make clear that I'm talking about not more, I mean, if you consider the biotropic equation, this is your vectorial solution, rho u. This is the flux of each quantity, this is entropy, and this is the flux of. Okay, so it's just putting these general things. Why? Because now I can talk about what was known on these kind of things. Well, n equal 1 is a scalar case. Well, a scalar case, everything is known. It's Krushkov theory, right? Everything is known. I will still talk a bit about it, but just one slide, because in some way, what I can say that what we are trying to do is pushing Krushkov to system, right? That's one way to to see stuff. So for this, well, what is Krushkov? Krushkov is that actually you have not only one entropy, but you can consider an entropy which compared to any, and let's say K is a constant for now, right? So you have a velocity and you compare to a constant. And the nice thing is that it is an entropy by itself. So when you integrate, it decreases. It means that it gives for free contraction for the L1 norm, right? So your constants have actually contraction property, right? And of course, because it's just scalar, actually you can modulate your constant here and show that actually when you have two solutions, you have a contraction property. So any V has a contraction property and everything contract in N1. And of course, this has a nice property. You can have propagation of BV norm and etc. But of course, it's just for scalar equation. So for system, basically, well, what was known is for small BV solution. So I didn't say BV is a way to measure the shock. So you can have shock, you can have discontinuities, right? But it's the sum of all the discontinuities. And you say they are small. So it's basically a perturbative of constants, but with passively discontinuity, right? And well, so there was a solution constructed by Klim, and there was this very nice theory put by Bressan 25, 30 years ago, in order to have actually those uniqueness of that in L1. Okay, so that was last century technology. And another, even older technology, which, so this is L1 because I mean, you will see that actually it's very important. But this was based because you compare solutions in L1. There was a compensated compactness, which is sometimes called L infinity theory. And well, that's a way to construct solution only for 2x2 systems. So here it's even for n by n. Anyway, I'm talking about 2x2. So the composite compactness is one of the case, and is a way to construct weak solution for generic L infinity. This means you don't have this BV constraints, but then you have no uniqueness there. And there was another one which was introduced by Dafermos and Eterna. And that we're pushing now, and which is based on L2, and that's I shouldn't say, yeah, that's what I want to talk about. So that's something we're pushing in a lot of direction, even some multi-D cases now. But in some ways, the result that we are more proud now is the limit of Navier-Stokes. So that's why this is the one I will concentrate today. If we talk now about limit of Navier-Stokes, so there was some results. So in the N1 theory, this result got a lot of popularity at the time by Bianchini and Bressan. And it was actually for general system to say that you can pass into the limit, but you see, I mean, it has to be what they call artificial viscosity. It has exactly this. This means that it has to be diagonal, linear. This means that putting a diffusion actually also on the density equation, and the rho u, it will be dxx of rho u. So it's not the Navier-Stokes. It's really this one. And it was stuck to here, I mean, for 20 years, right? It was stuck to knowing how to do it only for the vanishing viscosity case. In terms of composite compactness, so there was a result of Chen and Perepelitsa, when they were actually able to pass into the limit in the model I've shown, Navier-Stokes to Euler. But it is with composite compactness techniques that even if you are in the small BV situation, it's not known if you recover the limits, the solution constructing there. So that was basically the things. With the L1, you can have Inviscid limit, but only with non-physical model. If you take a physical model, then you can show that you recover an Euler solution, but you lose the hit. So that's where we went. So this is the result I want to advertise today, and I will just this one. So for technical reason, I need to introduce this mu. You remember it was viscosity functional, and for technical reason, we need it to be like bounded by the law, at least bigger than rho alpha for some coefficient, right? So for my defense, I can say we can take gamma equal 2 and alpha equal 1. And gamma 2 equals alpha equal 1 is actually what you get for shallow water equation, right? Not the bound by below, but actually the bound by above. So at least this is something that recovers this kind of strength, but it's not for that we do it. And if you want to know, you will ask, and I will say, but we need some behavior log. And it's really because we look with very wide solution, right? And we have to. We don't have a choice. So here's the situation. So the theorem, and I will say, so you fix a BV initial value. So it means density, velocity, small BV, in order to have the solution in the uniqueness at the Euler level, right? And then what you take is that you take a solution for the Navier-Stokes, and for the solution of the Navier-Stokes doesn't need to be small BV. You just have to converge strongly to the U0. So, I mean, if you're fine with the U0, fine. Well, but there is a little technical thing. It's the density has to have a slight regularization thing. It's nu times, right? So this means that it can blow up like 1 over nu, right? But we need just a slight regularization. So if you have a general value, it's natural to say, well, you want a convergence, right? But okay, so you take an initial value at the Navier-Stokes level, it converges to your small BV. You take the Navier-Stokes solution associated to this initial value, and it converges, whatever, strongly to the unique BV of the Euler associated to, I mean, small BV, right? So the associated to this problem. So that's basically solving the Bianchini-Bressan in the framework of this 2x2 system, right? But for Navier-Stokes. And I said, well, you know, they were stuck for 20 years here. So right away, we can see that we do something very different because I mean, what was the proof of Bianchini-Bressan? Well, basically, they had the uniqueness in their setting for the Euler in small BV. So the big part, and the part which was actually very hard, was to show that at the level of Navier-Stokes, for each nu, you control the small BV. If you propagate the small BV, well, you have enough things to pass into the limit, right? What I claim is that that's the thing that we don't use at all because we don't even need small BV at the Navier-Stokes level, right? So we don't do this at all. Right? What is important is that the limit of the initial value, but not at the Navier-Stokes level. So in some way, we say, well, let's forget about that. Actually, I think that's the problem. I think that this is a thing which is not true. You cannot hope to control BV for nonlinear general system, right? So you forget about that and you do something else. That's the thing. So not need small BV, right? So there is really something different here. There is also something interesting is that you can actually do a double limit. By this, I mean, you make a perturbation of the initial value, U0 epsilon, as first nu equal to 0. And what you get is a stability at the Euler level, L2 stability among limit of Navier-Stokes. And that's also something which was not technical. Okay, so everything is based on reviving in this situation the result of the Affiliation kernel. And let me write in a very simple way what is behind the weak strong principle of the Affiliation kernel. Well, is basically saying that Lipschitz solution to Euler are very stable in L2. And why I put very is because it's not mathematical, so I can put whatever I want, but it's really very, right? So very mean that, you know, even if you put perturbation in another, so you want Lipschitz, right? So usually when you take stability, you say, okay, if I take Lipschitz, I do a perturbation, which is Lipschitz. I mean, fair enough. But here, actually, the perturbation can be whatever. I mean, really weak, right? And whatever you do. And the principle is so simple and so powerful that actually, well, everything is controlled by this entropy. And you will go to L2. Okay. So, of course, you have stability. The first idea is with respect to initial value, but it's actually a very strong tool in order to have to have asymptotic analysis, and is to do perturbation with respect to the system. And here, well, I talk about Difference-Mitterrand. People sometimes look at me and say, no, it's Yao. So whatever, you put your Yao did this for Gitz-Borland. It's the same tool, right? I mean, as a tool. And people call it modulated entropy. And it was used to pass from Boltzmann to Navier-Stokes in compressible. It was by Saint-Raymond, Gauls, Lyons, Masmoudi, all those people. It was used in order to, well, recently by Serfati and Rosenzweig. I mean, it was from Texas, I should know, in order to get mean field limits. So it's of course, what is hard is not using technique, but it's the techniques that you put everything into it, right? And it drives the stability. You just have to deal with the details, which usually are the problem, right? But there is a telltale each time someone uses this kind of techniques. You can see it right away in the result, where they will say assume that the solution of the limit problem is Lipschitz or smooth on a fixed time, always. Because it's based on the super strong stability of Lipschitz solution of the limit problem, whatever is your equation. So what we're doing here, basic idea, I mean, that's when we began to work on this kind of things, is, well, to extend these things on BB solution. Things that actually solution with discontinuities may have the same kind of super strong stability with the L2 mode, which is not true. So it has to be a catch, right? But I will explain these things. So that was the first things. And I claim that, I mean, basically the first stage was reached a couple of years back. So again, this is first at the level of Euler, right? So at the level of the Inviscid. We work stability, well, with respect to the initial value before doing with respect to the system. So there's two papers because basically, I mean, this is really putting everything together, but all the technicalities, actually a very technical, but results that I really love. This one also, I should name. So Krupa, I mean, Gengchen. Gengchen knows a lot about the front tracking methods. That's why I learned everything from him. So he was working with Bressan. Sam Krupa and Will Golding are from a student of mine. Sam is now in Paris at the ENS right now and very strong. And Will is a postdoc at Chicago. And that was all the technical things that we call A-contraction with shifts. I mean, with shift could be orbital when you have one singularity, but it's more complicated when you have more. That's why we keep the name with shifts. I will explain that. Okay, and you know, when we reach this, I thought that was it. Because usually, when you understand really the problem, and you're not dealing with, I mean, you may have technical problem, but it's very natural to then see perturbation as perturbation of the system. Right? It turns out that when you have singularity, it's not true anymore. And it's not true anymore, there's still problem to make, and this is because of the operation of viscous layers. Actually, when you go, you know, when you have a solution which is Lipschitz, the viscosity is very, very small when you zoom in, because when you zoom in on your solution, locally, you are smoother and smoother and smoother, and the perturbation is really small. But now when you are close to this continuity, actually physically, you have something that appear, and this is this viscous layer, and those viscous layers, well, are very sensitive little thing, right? And the thing that I put it in red, because stability of viscous layers, there is a full, I mean, you can see there's a lot of work on that, right? But what people do when they look at stability of viscosity, what they do, they rescale and u equal 1, and they do small perturbation, stability, small perturbation. But what we need is stability uniform with respect to u. We need perturbation over the 1 when you look at nu equal 1. It's basically putting infinity energy at the level of the viscosity. That's what we need. And I will try to convince you that we need it. And it seems strange that it's possible, actually, putting infinitely many energy and still control things, but that's what we have. And that was really, really, really new then, right? Okay. So basically, I will try to give idea of these things. And the first thing is to come back to relative entropy in the context of Euler equation. And the idea is super simple, but very nice. So let's say you fix V first, you see it as a constant, right, or a state, and you want to compare two states. The state U, you take V. So what you do is you take the state of U, you compare the state of V by taking out the expansion, right? I mean, the expansion of the one of eta of E with respect to U. So it's basically a parabola, you take minus the line, right? And what you get is that, well, the difference is like a square because you are strictly convex, right? So you have something which controls, and that's why we call it the L2 things, that basically controls the L2. But on top of it, because at our view, well, you have an equation, and with these constants, this is a constant you don't care, and this is linear with respect to U, so you have an equation on this quantity, at least when you compare to a constant, right? So this means that similarly to the Khrushchev things, you have actually an entropy. For all V constants, you have an entropy. So it means that you have a family, hidden, you have a family of entropy that compared to any constant, well, it's just L1 is not L2. I mean, L2 is not L1, but which gives you a contraction. So you still have constants which are contractive for the L2 node. You say, okay, well then, I mean, Khrushchev should be okay. So what you know, you want to compare to BV solution. I mean, those equations are local, right? Because I'm still working on Euler. So you can say, I mean, I just need to understand when I zoom in on the things. If you zoom a BV function, either you're constant at the limit or you're a Riemann problem. So you need to understand rarefaction, shock, constant, and that of phase, right? And that's it. You put together and that should be done. So you look at constant, good, done. Contraction, rarefaction, well, not for any system, that's weird, but it turns out that we are happy for Euler, the rarefaction are contracted, right? So it's all about shock. It's all about shock. And, well, you don't have a contraction of shock, and it's not a scoop. That's why people stopped working on the L2 since the 90s, right? So there is problem with shock. So problems doesn't mean that everything is dead. So let me show you the problem. And for the problem, actually, the problem is not about the system. So I will show it on burgers. It's burgers here. It's a big U, but it's little U. It's just constant, right? So for burgers, I take a shock. And the shock is 1 here minus 1 here. I mean, very easy to see that it's steady, right? I mean, you take the square is 1, so dx equals 0. It's a solution. Okay, so you take this, and you take a perturbation, a very simple perturbation. The perturbation here is a solution, no perturbation on the right, just on the left, to simplify things, and is 1, epsilon, just 1 plus epsilon, so just a small perturbation here, and well, smooth there. Okay, so this means that if you compute, this is actually like the squared, right? This is like the integral of u minus s squared, epsilon squared times 1, epsilon squared, fine. And then you look at, you make this evolve, and you make this evolve, you can see that what you messed up here, I messed up with the Rankine-Hugoniot condition. So this means that now this singularity is actually moving, and it's moving with velocity exactly epsilon over 2. So this means that now you have a translation of your things here exactly with this distance epsilon t over 2. Right? So this means that if you do L2 now, is a square times the integral is epsilon t. So you go from epsilon squared to epsilon t, you can say, well, epsilon t is still small, not if you sum up, right? Sum of epsilon squared and sum of epsilon is not the same. And that's it. That's why it doesn't work. So it's really a problem of norms, if you want, because if you do this with L1, this is over the epsilon, this is over the epsilon, right? So it means that the L1 is better than the L2 for this things. Well, except if you want to work on Navier-Stokes or those things. But okay. So, but then okay. So you look at this picture and you say, okay, well, I got it. I mean, the position of your shock is very unstable, right, in L2. But you still want to be a shock, right? I mean, these things really look like these things. It's just you don't know where it is. So that's orbital theory. If you know this about stability, especially for viscous things, is to say, well, if you forget about the position, then you may have still something. And that's the thing that actually, so this was the first result in this direction. First direction. So here I write it for a system, a general system. Actually, we have it for one general system. But let's say for Euler it works. So you take a shock. So your shock, oh, I never put it a shock. I mean, a shock is just in 1D is, you have solution, so which is rho L UL, so the rho UL, and here you have another one, rho R UR. And this is a little u, because for me this might be UR, might be UL. Right? And so you have two values and it goes at sigma and sigma. Okay, so it's shock. There is a shock wave, and associated to this shock wave, so you fix the shock wave, there is some constant, A1, A2 here. I could put just one, but okay. A1, A2 positive, depending only on the shock. And now if you take any weak solution, I put good because you need testy conditions, strong trace, I don't want to talk about, we don't have this one, Navier-Stokes later. You can find a shift such that, well, you have contraction, the quantity decrease. And what is this quantity? Well, so you add this Y solution, the blue. I claim that there is an X of T here, then you can put your shock here, so it's UL, UR. And what is this quantity is the L2 norm is basically the L2 norm of U with respect to the shock, because here you integrate on the left on X of T, you integrate U with respect to UL, so it's almost the L2 squared of US UL up to the shift. And after the shift, you compare to UR, right? So if there was no A, is really, and not the X, it would be really the contraction. So it's contraction up to shift and up to weight. For scalar, there is no weight. That was actually the very first result of Bianchini. Was a student of mine. So, but for system, you can prove that you need the weight. You need the weight. But the weight depends only on the shock, and but the shift that we've seen, right? Even for very simple things, the shifts are here and they are needed, and you control them much. So what is behind this? It's very simple. I mean, it's basically, if you linearize your equation here, for the scalar equation is U going this direction, right? Here is U going in this direction. So basically, it's all the energy you want to crash in the middle. You just don't know exactly where, because of the shift, right? So for system, if you linearize, you have two directions, right? And if it's an extremal shock, here there is always two directions going in, one going in, one out. So what you do is you put a coefficient here small enough that what go out will be negligible with respect to what is crushing in the middle. That's one way to see it, right? That's one way to see it. But it's a very general principle. So, okay, so we have now contraction. We have contraction. Well, the best you can get, right? With respect to constants, rarefaction, shocks. Well, let's try to put them together. And that's what we did for the BV solution. So now, I mean, the idea is pretty simple. So because we know to do it only for simple waves, what we want to do is compare our weak general solution. I put U nu, but at this time is still just a solution of the Euler, right? Primitive. And you want to compare it to something which is piecewise constant, because piecewise constant, we know how to do it. Now we have the tools. So what we do is actually we construct a form tracking approximation of the Euler equation. but we construct it not with respect to, to the wide solution that we have, but with respect to the small bv, because we know that our initial value is close to the small bv. So we know that our initial value is close to small bv, and then we take this small bv here, and we construct the approximation of Euler, but of course we cannot compare to this thing. So what we do is we shift it artificially. And the shift depends on the wide. So we have the wide, and you do something which looks like Euler, except it's not Euler because I messed up with the Bianchini condition, and I make it move. So what I gain by doing this, is that this U bar delta here, the waves are not moving as they should. But when they interact, I still use the Gleam potential. They interact the way they should. So we keep the small BV structure. So this U bar delta here do whatever they want, but they stay small BV. And because we make artificial shifts, it means that actually I still control the distance of U0 to U bar delta. So what yes?
Are these functions x of t continuous?
Which function?
X of t, x1 of t, x2 of t.
That's a good point. They are not highly not unique. And the situation is why? Is because everything wants to crash in the middle, and it's pretty dramatic. So, there's a lot of casualties here, a lot of loss of energy, which means that you don't need to optimize the best. So if you wanted to optimize the best to say, well, I have some unique, well, at first it's not clear, but then you would be, you may have some job. But playing with the fact that you have some room, you can make them Lipschitz. So by construction, we keep them all Lipschitz, right? Which, yes, obviously is a big plus here. Yes. And we can make them behave like the wave. So there is another problem. Is in order to get the Gleam, okay, pushing was not okay, but the Gleam potential, one wave has to behave like one wave, and two waves have to behave. This means that one wave has to go always to the right and to go left or whatever the right direction, and two waves only on the other one, right? That was actually a very big thing. I didn't know how to do it. This Sam Krupa will fix that. Find a way to do this. And that's, of course, another very important point here. Okay, so what is the idea? Well, of course, I mean, when you want to do this, there's another thing, there is a weight, right? So each time you have things, I mean, we know that we have to weight the interaction. So this means that each time you have your family of waves here, you have to put weights, constant weights here. And when those weights are fixed, then you know that the things decrease. But each time, so the quantity, but each time you have interaction between two waves, you have new waves come in and out from that, and you have to reconstruct the weight because the weights are different. So there is all the game of measuring the weight, right? And to show that actually the difference of the weights are proportional to the size of the shock. And that was very technical, surprisingly for me, was extremely technical, and that's the paper of Krupa, Goldie, and myself, right? So this is this paper when all the technicalities there, which are extremely important, controlling the shift, and controlling the weight is here for small interaction.
The weight has to be positive?
And strictly positive too. Yes, exactly. So basically, I mean, we begin at 1, right? Because actually what's important is the ratio, right? So you begin 1, and then what you show is that each time you have a shock, your weight is of order of the shock, and because of the weird things that you're constructing here, but because it will be small bv at the end, it will be 1 minus a little bit, 1 plus a little bit, and constant. Exactly. Okay, but what you get at the limit of U delta is really, really weird, not controlled, right? Because you can, I mean, this source shift can even change the order of waves interaction. I put little things here. So this is xt. So this means you're constant. So if you do exactly the solution of the phone tracking, well, your interaction move linearly here, right? So it's really this going that way, right? And but now with your shift, I mean, everything is shifted. So maybe those two ways were supposed to meet before meeting the first one, but actually maybe they will meet the first one before meeting the other one. So very, very, I mean, it's not only that it's a differential Rankine-Hugoniot condition. I don't know what it does, right? And that was at one point the leap that we have to say, well, we don't care. What we want is retrieving by this, not the fact that your solution is retrieving the structure, the small b. That's the important thing. So we track something that keeps the small bb because each interaction follows the control of them. And because we do the shift with respect to our real wild one, that stay close. So it's basically what we get is the control of the non-BV part, right? Because if we take in some ways a projection on small BV and you say, well, the part which is not small BV, we control it in nature. That's what we get, not more. From now, I mean, for everything I do. Okay, I say this because everything, I mean, from the beginning, you see the philosophy is I don't control the shift. Those shifts are whatever, and I don't care. I work without it, right? And I get what I get. I say this because now there's Sam, who actually is reworking all those things, getting control on the shifts that I didn't expect it, and trying to go further in controlling them, right? So the control is not that good, but he managed to do things. I'm still surprised. But for everything I do, I don't want to see those shifts, right? That's basically, that was the philosophy. So that was I wanted to say. So it's a non-BV part, right? Because I control, I mean, if you want to control the inf of my solution minus a BV, you just need to construct one BV that makes the deal, right? So I control a BV and show that with respect to this BV, I don't know what is this function, but I control the size. So if I optimize, it will be even better, right? So that's basically the idea. So it's not a good approximation, okay, but it stays uniformly small in BV, and I control the non-BV part. What I do with the nice BV, well, I just take the Bressan theory out of the box. That's basically the idea. I will use it. Something differently now, far nicer. But that was the theory. Okay, so that's good. That's stability, the weak BV principle with respect to perturbation of initial value. Now we want to go to nothing between. Okay, we want to go to Navier-Stokes. And for Navier-Stokes, it's a wall here, and this was because if you want to, because of the function of viscous layer. So what is viscous layer? Well, if you take a real shock, well, if you look at nu fixed, then actually it's smooth to bit, right? I mean, that's super simple. That's what you have, right? But if you want the stability of those things, I mean, it really depends on what's happening. There's a very non-trivial balance between the hyperbolic term and the viscous term. And if you think about stability of shocks at the Inviscid level is everything crashing in the middle, then viscous is really, really bad because it puts you out. Right? So you have a perturbation, is actually push your perturbation out. And that's really, really bad. I mean, surprisingly bad. So, but it's even worse than that, is that what we want, I mean, you see, I mean, the idea will be to make to do a font tracking for the general solution at the Euler level. You will have an error, which is due to this, let's say delta, and then you have nu. But your nu will be extremely small, and it will be important, you will see just after, with respect to your delta. So you have an error with respect to your scheme, and you want to have to control your layers for extremely small nu. And that's why you need, with an error here, at this level, you want a perturbation over the delta for nu small, uniformly with respect to nu. So you know that your perturbation, there is a complex interaction at the level of the viscous, I mean the viscous thing. So it's very natural to rescale. You have to rescale to order 1 to see the interaction between the two. But if you rescale, which is nu t nu x, I mean simple, right? Now it's order 1, and you look at the initial perturbation, well, there is a change of variable, which is, well, 1 over nu. right? So it's a square root L2, so square root. So you end up with an initial error, which is delta of square root of nu, which is basically to say that the kind of stabilities you're looking at here is by putting all at the scale of the layer is put it actually infinite or up to infinite energy there, right? And what we can is that actually we can control this. And how we do it? Well, is basically by looking at contraction. If you have a contraction, and it does not, if it is basically stability with large perturbation, it means that if you have a contraction, whatever the size that you have at equal to 0, well, the size is the same. So you rescale, if you delta, you stay around the delta. So it's repackaging the stability by a contraction, but a very different situation when you have extremely large energy. And if you have extremely large energy, I mean, it's bad, but for a lot of things. It's bad because you lose L infinity. You don't have uniform L infinity norm for Navier-Stokes. You have it for Euler, not for Navier-Stokes. So you have to work not only when things are small, but when things are very big, very small, and that was the conditions that we need. Okay, but even when it's small, it's different. In order to pass, there is basically two regimes here. There is a regime where the perturbation is of order of nu, and that's what people look usually. I mean, at this level, so it will be order 1. And usually what is important is the linearization, right? You have to understand the linearization. Then there is when the perturbation is of order of the size, because actually we do it again an asymptotic limit, but in the side of the things. And is when your perturbation, right, will be of the size here. And weirdly, we need to go to the order 3. So it's not on the order 1, but you have to derive order 3 to consider this. And finally, there is when the values are very big, which is very different way to control them, which is very more brutal, and where we need this growth of nu is exactly to control what's happening. But things are very big. Okay, so that's the things. If you manage to get this, then the idea is then, well, we want to put everything together. And here's a general strategy. So the general strategy is to say that, well, I mean, at the end, we want to have the limit nu converge to 0, so we'll be close to Euler, right? So we go to Euler and we say we will construct a phone tracking for Euler, not for Euler first, right? So because the waves, if you don't have too much wave, they should especially for interaction of waves, they should follow this. So this gives you an error delta right away due to your approximation. And for this delta, then you want to consider very, very small viscosity. And why? It's because you really, really want to say that it's Euler, which is at first order. So if you're Navier-Stokes, now all your waves are interacting to each other. So you want to say that, well, but the interaction is with respect to nu, right? Because it's exponential minus nu over x. So you want to have, now that you have, the delta fixes you the number of waves, right? The number of waves that you will have. It's extremely big, but it's fixed. So then you take a nu very, very small to be able to compare the non-locality of your waves, well, at least when the waves are not too close. So when you do this, then, of course, you want to run the A-contraction, but for the A-contraction, I mean, this is Navier-Stokes, so you have to compare not with respect to the Euler, but to the layers. So this means that you take your Euler object, you have your front. From your front, you change your front by your viscous front, right? And as long as the front are far away, it begins to make them move with respect to your Navier-Stokes solution, right? Because the shift depends on your Navier-Stokes solution, the wide one. And you do it in order to control the N2. So you make all things move. But what happens when they become too close? So when you have two waves, they become too close, and we put nu 1/3, which is important, it's very big compared to nu, right? There's a range of things. So they become too close, so now they interact. But they will interact on a very small time because they are up for collision, right? They are actually coming to each other. So for a very small time, we do not control nothing. And what we say, well, we do not control nothing, but because it's a small time, then we free them, we make them interact at the Euler level, because here we know how to solve the Riemann problem. We push them a little bit, and this hierarchy is not that big because it's a small time. And then we reconstruct our weight, we reconstruct our front, and we make them fly again. And during the flight, we control the contraction. And we do it again. Right? And all the game is to see that actually we can control everything. Okay, so that's the way we do it. What we gain by that? Well, everything is done such that the front, well, so you see, I mean, the front, they just move at weird things, right? And they are viscous, but each time they interact, we go back to Euler and we make them interact, and we know that we keep small BV for these things, which is not an Euler solution, right? But we don't care. Right. So what we control is we control a weird thing, which is small BV, and what we control is the control between Navier-Stokes and these things. When I say converge to zero, well, because at the end the delta will converge to zero, but we control the non-BV part, right? And that's what we wanted to do. So here we end up with slightly one more. A problem is due to the shift. So you asked, are they smooth? Yes, they're smooth at nu fixed. And the problem is what we end up here is in the Euler case, I assume that my solution will banded, which is fine because you can take solutions which are banded. If they're banded, not only they're Lipschitz, but on top of it, they're finite. I mean, the thing. So you control the shift at least in L infinity, so it means that you control the BV solution of this thing shifted in time too. But the problem is that Navier-Stokes, the Navier-Stokes is bad already for that. That's already a difference between your non-physical model and your Navier-Stokes. You do not have uniform bands with respect to nu. So your velocity can be extremely big or extremely small. And so at the end, we can have some very weird oscillation in time. So we control the BV things, but this solution behaves very bad, may behave very badly. But okay, we just throw everything we have, and here we go. So this is what you had before, right? I mean, you know that you knew conversion U bar in zero. Okay, so this is the real Navier-Stokes. This is made up weird things, which say small BV. But we don't know if this converges strongly. So where we do it, well, we need to pass into the limits, and we go back to jet peripelization. So it was not enough to use the contraction. We use also the composite compactness. And the composite compactness will say that this U converge. So because the difference converge strongly, U bar converge strongly. And that's the additional thing that we need. Of course, at the end, you keep the structure. So by a combination, so in some ways, the A-contraction is always just to keep the structure. The contraction gives you the fact that you are small BV. You retrieve the fact that you're in a solution at the end by the composite compactness of Wischiang and Peripelization. Yeah. And then, well, you end up saying that you have the right solution at the end, because at the end you have to be really solution. So just take Bressan, right? So in some ways, this L2 thing it's just something put on top. Yes.
U delta here is U delta nu. It's viscous.
Yes. Yes, you're right. I mean, I've been very, very rough here. At the end, the layers, right? The difference between the layers and the not layers is extremely small.
But so how do you make U delta nu out of U delta?
And so exactly. So the U delta, I mean, let's say at equal to 0. So at equal to 0, I have my weird solution, which is close to a BV1. So I take the BV, and the BV, I replace it by piecewise constant with a little error of delta. I have that. Now I solve my Euler. So at t equal to 0, we have all those nice fronts. And those nice fronts I want Navier-Stokes. So I replace by viscous front, all of them. So I'm cheating because it's not the solution of Navier-Stokes, even if, because, but what I do is that because they are separated enough, and I put the nu extremely small compared to the number of waves. So this means that the interaction, the fact that they are not on Navier-Stokes, because the interaction between all the waves are extremely small, it's exponential.
So you just literally add layers.
I add layers. But again, that's why I really need to have stability uniform with respect to nu. Because it really means, you fix your error, it fixes your number of layers, and now you just want to add your layers, right? And that's extremely important for the simplified. And of course, where they begin too close, and here I forget about Navier-Stokes, and that makes interact through Euler. Basically, why it works is because you just need to make them cross. That's the problem. You make them cross, and then after that you control them. And there is no. If you want to make two waves cross with conservation, well, that's the Rankine condition. This is actually solving Euler, right? And so you just make them cross, and then you can control them with respect to things.
And because you put the shifts, you're not able to just say you're close to a usual front tracking solution.
Not even, yeah.
Okay.
So
otherwise you wouldn't need to actually go through this extra.
Exactly. So exactly, because I need three things. I need to say I'm close to BV. That's a contraction. I need to say, well, when I will be BV, I know what to do when I'm BV and the solution, and that's Bressan. But I need to say why I get a solution at the end. Well, that's where we used as a black box the chain Perepelitza.
Mm-hmm.
But not on this, but at the end, because they converge, and the difference converge to zero, right? So these things converge to the same. But it's really
so you want a BV solution, and then the shocks will satisfy all of the conditions.
At the end, yes.
Okay.
But we don't know how. We don't know how. It's just because we can pass into the limit in the solution itself. Yes, exactly. And well, its conclusion, I mean, that's the end. Thank you. So, sorry, yes. So that's something we did for this kind of problem. Now we're trying to do it for other problems. Now we have the stability limit, Inviscid limit for multi-D entropy waves. We're trying to get things in multi-D. So in some ways, the beginning of it, right? I mean, we have something that's in the end. Thank you.
Questions? What happens if you have a more complicated Euler system, like for instance?
So the weak BV, we have it. So I mean, what's happening if you have a 3x3, right?
Yeah.
So the theory of general shock, and you have a weight and everything goes is for what we call extremal shock. So if you have 3x3, there is another family in the middle. Mm-hmm. For the full Euler, it turns out that this middle family has also a nice structure, but it's not, everything we do is by perturbation. So if you take A close to 1, I mean, there's a family of A. For the compact discontinuity, there's a unique one, and the temperature of the state. So you put the temperature of the state, and you have the same structure. So something that's Denisser, I mean, I think I'm not sure, but it's Denisser who find it, who find this structure. So this means that you can do the whole same thing. Now you have all the waves, you put them together. We don't know how to do it for the limit Navier-Stokes, and it's for very technical stuff. All the hard part of the proof works exactly the same. What we do not control is because you don't control in infinity. But the problem is when the density, temperature is extremely big. We have no way to control that. That's the problem. We could put if theorem. If you know that Navier-Stokes Fourier, everything stay in ball in infinity, then we should be able to do this.
And why is this coercivity in the viscous coefficient so important?
Exactly this.
You?
Exactly to control big values. I mean, it's very pedestrian, right? If you have a mu of rho in front of it, well, when you take the
when you
energy, you have mu of rho, the square mu is bigger, you have more to the estimate. Very pedestrian, right?
But then it doesn't seem you actually need the upper bound. I mean, this,
Sorry. Yes, a lower bound. We need a lower bound for big rho. We need the lower bound for big rho. That's what we.
But you put both of them.
Yes, because that's the thing. I mean, there's flux. So when you integrate, there is a good term. But if you multiply by a function of x, you have also to integrate by part. You have also to control it. So it's
okay.
You need the good, but you need also to
Okay.
control the bad. So it's. It's a thing. But I mean, that's something that's weird. I mean, usually when you do stability, you don't care about those things because everything. I mean, you linearize, so you need everything to be close in infinity. So you work with a Hn big enough. You control an infinity. You work locally, and that's it. But here, because of this uniform nu that we have, we cannot work with more derivative. If you had one more derivative, then you lose just the scaling effect, right? And so because of that, you do not control. So if you add it at the level of the equation, fine. If you put a non-viscous and a non-physical term, then actually you keep the n infinity at the higher level. Super. You keep your estimate. But if not, this destroys the infinity structure.
Any other questions? Well, if not, thank you.